In this video, we are going to learn the rules of nomenclature. In the early 20th century, organic compounds were named on the whims of their discoverers. As the number of known compounds grew, a systematic nomenclature system was required. Today we name compounds according to the rules designated by the International Union of Pure and Applied Chemistry, or IUPAC. The best way to get comfortable with IUPAC rules for nomenclature is to practice. Alkenes are compounds that are composed of only carbon and hydrogen. In the functional group video, we discussed that these compounds are fairly unreactive. Haloalkenes will have carbon, hydrogen, and a halogen. A halogen will be considered either fluorine, chlorine, bromine, or iodine. Nitroalkanes will have a nitro group and NO2 group. Cycloalkanes, again, carbon and hydrogen if they don't have a substituent and they are in a ring. And ethers will have the functional group alkyl, oxygen, alkyl, where R and R1 do not have to be the same. They can be the same, but they do not have to be. So this is one of the things that I'm going to tell you to memorize. You need to memorize Table 1A. These are the parent names for the compounds that we are going to name. Once you have these memorized, we can look at the different substituents and determine how to build an IUPAC name from there. Here we have two alkanes. In both alkanes, we have a chain of 4 carbons. In the first alkane, that chain does not have any substituents, so it is just going to be called butane. The second molecule has a substituent or branch point. What we are going to do in the rest of this video is learn how to name molecules with substituents or branches. The 2 rules that we have to keep in mind for now are that we need to identify the longest continuous chain of carbons. That is going to define the root name or parent name. And then we have to assign locants to the substituents, and those substituents will either be alkyl, halo, nitro, or epoxy substituents. They will be listed as prefixes with the number in front, and they will be listed alphabetically. So as I said in the beginning, the best way is to practice. So now we're going to practice. So here we have an alkane with a halogen substituent, and that halogen substituent is a chloro group. We need to find the longest continuous chain of carbons. Okay, so let's look here. Here is a continuous chain of carbons. It is the only chain of carbons, so let's number it. 1, 2, 3, 4, 5, 6, 7. You want to give the substituents the lowest possible numbers. Here there is only one substituent in the form of the chloro group, so that when we assemble the name, it will be 3-chloro, and if you remember from table A1, heptane. So you're only going to have a dash between the location and the prefix of the substituent when there's one substituent. We'll deal with what happens with multiple substituents after a couple more examples. Here are two more basic examples before we move on to multiple substituents. Again, you want to find the longest continuous chain of carbons. So here, that would be highlighted in red. And if we count, there are 1, 2, 3, 4, 5, 6 carbons. That nitro group is in carbon 1. So this would be 1 nitrohexane or nitrohexane. You don't always have to designate the one position. Let's look at the second example. We need to find the longest continuous chain of carbons. At first glance, it might seem that what I've highlighted in blue is the longest continuous chain of carbons. However, if we look again, we'll see that the longest continuous chain actually has 6 carbons, and you can see that highlighted in green. 1, 2, 3, 4, 5, 6. So again, you always want to find the longest continuous chain. So here we have 3-methylhexane. So now we're going to look at some examples where we have more than one substituent. When you have multiple substituents, particularly if you have more than one of the same substituent, you will use di, tri, tetra, or penta, which indicates 2, 3, or 4, or 5 respectively, for the substituent. These prefixes will not be considered when alphabetizing and assembling the name. You need a location or a number for each substituent on a chain. You also want to make sure that you have the lowest possible numbers for the substituents. What this means is that if you have different possibilities for numbering your chain, you want to choose the one that gives you overall the lowest numbers for each substituent. Let's look at this example. First, we should identify the longest chain of carbons. The longest chain of carbons is a propane, where you have 1, 2, 3 carbons. Now we have to assign numbers to the substituents. So we could number 1, 2, 3, or as shown in green, we could make the carbon with 3 chlorines carbon 1, carbon 2, and then the carbon with the fluorine, carbon 3. Let's evaluate the yellow scheme. If we use the yellow numbers, it's 1 fluoro, and then 3, 3, 3 trichloro. If we use the green numbering scheme, it's 3 fluoro and 1, 1, 1 trichloro. As I said on the previous slide, we want to choose overall the lowest possible numbers. The lowest possible numbers come from having the fluorine on the 3rd carbon and the 3 chlorines on carbon 1. So when we assemble the name, it will be 1, 1, 1 trichloro dash 3 fluoropropane. Here's another example. First thing you want to do is find the longest possible continuous chain. Here we have 1, 2, 3, 4 carbons is the longest continuous chain. Now we have to assign a numbering scheme. If we number 1, 2, 3, 4, or we can try an alternative scheme where we have 1, 2, 3, 4. Let's evaluate the green scheme. It would be a 1 bromo, a 2 bromo, and a 4 bromo, a 3 nitro, and a 4, 4 di iodo. Now, when we would do the name here, it would be 1, 2, 4 tribromo. Let's look at the red scheme. With the red scheme, we have a 1,1 diiodo, a 1 bromo, a 2 nitro, a 3 bromo, and a 4 bromo. And again, the bromos would come together and make 1, 3, 4 tribromo. So we want the lowest possible numbers. Overall, you would get the lowest possible numbers if we use the red scheme where you have the 1,1 diiodo. So when we assemble the name, we have to alphabetize. So the name would be 1, 3, 4 tribromo dash 1,1 diiodo dash 2 nitro butane. Now let's try some examples where we are naming compounds with alkyl substituents. If we look at the first compound, we have to find the longest continuous chain. The longest continuous chain has 1, 2, 3, 4, 5, 6 carbons. The substituent is on carbon 2. The substituent is a methyl substituent. It has 1 carbon. When you are looking at alkyl substituents, what you do is you look at the corresponding alkane. Since a hydrogen is dropped when it is a substituent, you simply drop the ane and add YL when you have the substituent. So here we have 2-methyl hexane. Now, what happens when we have a branch substituent? So a methyl group would be considered a linear substituent. So here I drew ethyl, which is also a linear substituent where you have 1, 2 carbons. So the squiggle is meant to represent the main chain. Let's look at the molecule below. Here it's very clear that we have complicated branched substituents. And the branched substituents, as your book points out, have their own unique IUPAC names. You name the substituents using the same IUPAC rules that you would use to name a larger alkene. So the first thing we need to do is find the longest continuous chain. We could have the longest chain here. We could have the longest chain here, or here in blue. We need to count carbons. Let's start with red. Red, we'd have 1, 2, 3, 4, 5, 6, 7. If we did the green, we would have 1, 2, 3, 4, 5, 6. Well, that's just too short. Now let's try the blue. 1, 2, 3, 4, 5, 6, 7. So we have 2 chains where we have 7 carbons. We need to choose which chain is going to be used to assemble the name. You always want to choose the longest chain with the simplest substituents. So let me redraw the molecule. Let's look at our path in red. If you look at our path in red, we would have two substituents. An ethyl substituent, 1, 2, and then this complicated branched substituent. The way we would name the branch substituent is we would look at how many carbons are coming off the main chain. So in red, I highlighted the main chain, and then we would have 1, 2 carbons. There is a methyl substituent on carbon 1, so the branch chain would be named 1-methyl ethyl, and it would be in parentheses. Let's look at the blue path. On the blue path, we also have 7 carbons. But here, our substituents are much simpler. We have a methyl, we have an ethyl, and we have another ethyl. So we are going to choose the blue route. In numbering, this will be carbon 1, 2, 3, 4, 5, 6, 7. So when we assemble the name, we will have 1,4-diethyl, 2-methyl-heptane. Let's practice. Let's practice naming a branch substituent. If we look at the longest continuous chain, we'll see that the longest continuous chain of carbons is what is highlighted in red. 1, 2, 3, 4, 5, 6, 7, 8 carbons. We could also number 1, 2, 3, 4, 5, 6, 7, 8. So we have to choose blue or red. Let's look at the substituents. For red, we would have on carbon 4 a propyl group, and on carbon 5 a branch substituent right here. There are 2 carbons in the longest chain coming off that branch. So again, this would be a 1-methyl ethyl group. In blue, if we were to number blue, it would be 4, 1-methyl ethyl, and then 5 propyl. Both give us a 4-5 substitution pattern, so we have to choose. We're going to go with path blue because of alphabetization. 1-methyl ethyl comes before propyl. So the name would be 4,1-methyl ethyl, 5-propyl octane. So here I have drawn cycloalkanes. Cycloalkanes are rings with carbons and hydrogens. They are named with the prefix cyclo and then the parent's name of how many carbons are present. So the first structure would be cyclopropane. The second structure would be cyclobutane. The third structure would be cyclopentane. And the fourth, cyclohexane. If you have a cycloalkane as a substituent, so the squiggle represents a main chain with the ring coming off, you drop the ane and it becomes a cyclopropyl substituent. So similar to what happens when you have an alkyl substituent. So here we have a cycloalkane. We need to decide if the cycloalkane has more carbons or if the carbon chain coming off of it has more carbons. If you look, we have 1, 2, 3 carbons on that chain, and then we have 1, 2, 3, 4, 5 in the ring. So the ring is larger, so that will define the parent. So this will be a cyclopentane. Now we have to name the substituent. I'm going to see if I can erase these numbers here. All right, so to name the substituent, we have to look at the longest continuous chain. This will be considered a branched substituent, and this is the connection point. So we've seen this multiple times already. It's 1, 2, and then you have a methyl group. So this would be 1 methyl, ethyl, cyclopropane. And I have to put the 1 methyl ethyl in parentheses because it refers to the branch substituent. Now let's look at these 2 alkanes. In the first one, the longest continuous chain of carbons is larger than the ring, where we have 1, 2, 3, 4, 5, 6. So this would be a 3-cyclopropyl because it has fewer carbons, hexane. Now, if we look at the bottom structure that I drew, this one's a little tougher. We need to determine the longest continuous chain. So if we look at this branch point, we can consider we have 1, 2 carbons there. Or you could say you have 1, 2, 3, 4, 5 carbons. However, in order to name this unambiguously, we are going to say that we have substituents off of the ring. So here, this is going to be a cyclopropane as the parent name, and then you're going to have a methyl substituent and a butyl substituent. So let me just erase my numbering so we don't get too confused. So here we would have a methyl substituent and a butyl substituent. So it is going to be 1 butyl, 1 methyl, cyclopropane. Butyl comes before methyl alphabetically. Now we're going to name ethers. If you remember from our functional group, an ether has the formula ROR prime, where R and R prime do not have to be the same. They can be the same, and you have an oxygen in the middle. We are going to name these as epoxy substituents. So you're going to find the longest chain, and that will define the parent name, and then you will list the epoxy substituent. Now at times you may have to give a location. So if we're naming this ether here, the longest chain has 3 carbons. So this would be an ethoxy substituent. So this compound would be ethoxy propane. So just to complicate your lives even further, you're also going to have to be responsible for some trivial names of alkanes, alkyl halides, and ethers. Okay. From the alkane perspective, sometimes butane is known as N-butane. The IUPAC name for the structure that I just drew would be 2-methyl propane. It is also known as isobutane. Pentane can also be called N-pentane. Then when you have this following structure, which would be 2-methyl butane, it is commonly referred to as isobutane. pentane. And finally, if we have 2,2-dimethyl propene, it is commonly referred to as neopentane. So you have to be familiar with these trivial names. So if you notice in the previous slide, I said familiar with. Now we are going to look at branched substituents with trivial names or common names that you have to memorize. Now, I'm not making you memorize these to be cruel, but I'm making you memorize them because you are going to encounter them. So let's start with the simple ones. Here we have a propyl substituent where you have 3 carbons, 1, 2, 3. Again, the squiggle is the main chain. All right, it would be the longest continuous chain. And carbon 1 would be the point of attachment. In the second structure, where we also have 3 carbons, you can see that the point of attachment, so that's carbon 1 and then carbon 2, right? That's your longest continuous chain. So there is 1 methyl group, and we've encountered this before. This would be the 1-methyl ethyl. The trivial name for this would be isopropyl. And you will see this ingrained in the vernacular of organic chemistry. Now let's look at the next set of branch substituents where we have a total of 4 carbons. The first one is a linear chain, 1, 2, 3, 4, and would be known as a butyl group. The second substituent, and I purposefully drew these differently than what you see in the text so that we get used to recognizing these. If we look 1, 2, 3. So this would be 2-methyl propyl. This is known as isobutyl. All right. You can think of it as similar to isopropyl, but with just 1 extra carbon. Let's look at these last 2. Again, there's total 4 carbons. 1, 2, 3. This would be a 1-methyl propyl substituent, and it is known as sec-butyl. The last substituent, there would be 1, 2 in the longest continuous chain, so this would be 1,1-dimethyl ethyl, also known as tersh-butyl. So how did we come up with these names? We are going to learn about primary, secondary, tertiary, and quaternary carbons. These are particular types of carbons. So if you look at the blue carbon, and we see that it's bonded to only one other carbon, which is shown in black, we have a primary carbon. Let's look at the next carbon. You can see the blue carbon is attached to 2 carbons, so this would be considered a secondary carbon. If we go to the third structure, we can see that blue carbon is attached to 3 carbons, and that would be a tertiary carbon. And finally, we have the blue carbon attached to 4 carbons, and that would be a quaternary carbon. If we were to look at these in our bond line structures, we would see that this would be a primary carbon, primary, primary, primary. This here would be a secondary carbon because it is bonded to 2 other carbons. Then we would have a tertiary carbon because this carbon is bonded to 3 carbons. And finally, we would have a quaternary carbon because we have 1, 2, 3, 4 carbons attached. This is how we derive the names sec-butyl and tersh-butyl. So let's redraw what that branch substituent looks like. So in both of these branch substituents, you have 4 carbons where you get the butyl. Here, the point of attachment to the main chain would be a secondary carbon. Hence, we have sec-butyl. And the structure to the right, again, 4 carbons, but the point of attachment is a tertiary carbon. Hence, the name tersh-butyl. So you have to memorize isopropyl, isobutyl, sec-butyl, and tersh-butyl. Finally, we are going to come to the trivial names for the ethers and the haloalkanes. The trivial names from the ethers derive from the fact that you would just name each alkyl substituent and then add ether. So for example, here, this would be diethyl ether. You just need to be aware of the common names. I'm not going to have you memorize them. These are the 2 haloalkanes that you need to memorize the trivial or common name for. The IUPAC name for the top one is dichloromethane. Its trivial name is methylene chloride. You need to memorize this because you're going to see it in lab and you're going to see it both ways, and I'm going to interchange both names. So you need to be able to realize that they are the same thing. The final compound where you have to memorize the trivial name, here the IUPAC is trichloromethane. Common name for this is chloroform. Again, you have to have this memorized because most people don't call it trichloromethane, they call it chloroform. So that's it for your nomenclature. We're going to practice lots of nomenclature problems during recitation.